Hey guys, I'm back. This is actually the same part two, continuation of what we were talking about before. So I'm going to be talking more about uh, the vector database uh, based on this slide. So here, now what we are going to be covering is just to understand that vector database is going to be very crucial component of the RAG building block because most of the data that we're going to be using for our analysis is going to be mostly unstructured data, and those has to be actually stored in chunk, and they have to be stored in a vector database. Okay, and that the reason is because obviously you need the embedding added into the data itself. So that needs to be put alongside the metadata, and it serves faster similarity search across millions or billions of vectors. Okay, so the input data for most of the vector database is going to be vector plus the metadata, that is the source and the chunk ID and the permission, and the output is going to be the ranked nearest neighbor results for a query vector. Now, the advantages that you are going to be seeing over here is that there's going to be a sub-second search at scale via ANN indexes, that is HN, SW or IVF. You have supports metadata filtering alongside vector search. Many offer hybrid, that is the keyword plus the vector plus the keyword search natively. Okay, so the most of the common tools that you're going to be seeing in the vector database is Pinecone, Weaviate, Milvus, Qdrant, pgvector, Chroma, Elasticsearch, OpenSearch. Those are all basically vector mode type of database system, and this is going to be useful for storing all of the chunks, embeddings, vectors, and metadata. Now, the challenge that you are going to be seeing in the vector database system is mostly in terms of the index rebuild cost as the data grows. Okay, the recall and latency trade-offs in ANN tuning. That is definitely one of the other challenges that you might have going to face when you get choosing or selecting what kind of vector database you're going to be using. The multi-tenant isolation and access control complexity. Okay, so one of the examples you can think of is a million document enterprise knowledge base uses an HNSW index in a Qdrant to return the top 20 nearest chunks in under 50 milliseconds. So that's what we're dealing with. Let's talk about retriever. Okay, now retriever is also an important part of the RAG system, which basically takes a user query, okay, transforms it if needed, and fetches the most relevant chunks from the vector database. That is the full detail in section 8. So basically what happens in retriever is that the user input or the user query that is going through the conversation history is going to be the input. Okay, the the input then gets transformed into the output, which is going to be the rank list of top k the relevant chunks. Okay, so top k is again one of the parameters that we use in LLM models to select where what is the probability assigned for each of the chunks, and which one has the highest probability, and it's going to rank all of them and provide the top k relevant chunks. Okay, so the advantages that you're going to see over here is that it can combine dense and sparse signals, the mostly the hybrid. You have the re-ranking that improves the precision at the top, and you can apply a metadata filters like date, department, permission, etc. Okay, so the common tools that is used for retriever is the LangChain retriever, okay, LlamaIndex query engines, coherent re-rank, and cross encoder models. Okay, those are part of the retriever common tools. The challenges that you're going to face over here is the query document vocabulary mismatch. Now, top k tuning affects both the recall and prompt size. You have the multi-hop question, which need more than one retrieval pass. Okay, so those are probably the challenges that you're going to see on the retrieval side. So the example that you can think of is that what is my portfolio exposure to AI stocks. So the retriever pulls the client's holdings, sector tagging, research notes, and the compliance definition of AI exposure. Okay, let's go to the prompt construction. Now, prompt construction is mostly in, I think, the the purpose is basically to guide the user to understand, how effectively they can prompt the LLM model so that they can get the best result. Okay, so basically what it does is assembles the retrieve chunks, the user query, the instructions, the formatting rules into a single prompt for the LLM. Okay, usually again, this is definitely something that the user query has to be optimized in order to make sure that the output comes out in a more in a more concise and more formatted uh, manner. The input makes a big difference. So the top kid retrieve chunks, the user query, and the system instruction, those are very important inputs to the prompt construction, right? And the output is going to be single structure prompt within the model context window. Now, the advantages that you see over here is mostly going to be enforces grounding instructions, that is answer only from the context, and then it enables citation formatting. It can inject few short examples for consistent tone. Now, the common tools that we use for prompt construction is prompt templates in LangChain and LlamaIndex. Okay, Jinga 2 templating, custom orchestration code. Like these are probably some of the most common tools that we use for prompt construction. Now, the challenges that you see on the prompt construction side is the context window budget limits, so how many chunks can fit in, the prompt injection risk from retrieved content, the ordering of chunks can bias which the model tends to. Okay, so the example over here is that a template inserts each retrieved chunk with the citation tag followed by answer only using the search above. Cite the source ID for every claim. So that's probably one of the examples that you can think of in terms of prompt construction. Okay, let's go to the next part, which is basically the end of the building block, which is the last part, which is the LLM and the generated answer. Okay, so the language model synthesizes a coherent and grounded natural language answer from the constructed prompt. Okay, full detail in section 9. Basically what happens is that you have the assemble prompt, which is the context plus the query plus the instructions. Okay, and that has to be given out into a final natural language answer, which is ideally with citation. Okay, so the advantage over here is that you have the fluent coherent synthesis across multiple sources. You can summarize, compare, and reason over retrieved facts. You have the temperature and decoding controls tune creativity versus the determinism. So these are the advantages that you're going to have, like fluent coherent synthesis across multiple sources, can summarize, compare, and reason over retrieved facts. The temperature and decoding control tune creativity and versus determination. Now, Chat GPT or the GPT-4 and GPT-O, Claude, Gemini, Llama, Mistral, these are all frontier models that are constantly being updated, but those are going to be the common tools in this case. It can be served via the API or the self-hosted, right? But you're going to be using mostly the frontier models that are coming up, as latest developments are made in the LLM models. Now, the challenges that you're going to see is the model may still ignore the context and hallucinate. Okay, poor grounding. Long context can dilute attention to the most relevant chunk. The latency and the cost scale with the context length. Okay, those are the challenges that you're going to be facing in this particular case. Okay, so the overall recap that we're going to have is that the building blocks of RAG system, you're probably going to have 9 components, okay, split into the offline indexing path and an online query path. The data quality, which is the sourcing plus the cleaning, sets the ceiling for everything downstream. You have the chunking and the embedding, which determines what can possibly be retrieved. And you have the retriever and the prompt construction, which determines whether the LLM actually uses what was retrieved. Okay, so one of the knowledge question that you can ask is, which two components sits on the offline indexing path rather than the online query path? This we have discussed in the chunking and embedding portion of the slide, so you should be able to answer that. And along with the data source and cleaning, they run both index build time, not per user query. Okay, so that's where basically those two components are used, especially in chunking and embedding portion of the build out on the rack system. Okay, so this is the overall recap of the the building blocks of rack. We're going to be discussing the rack pipeline in the next session.